First, I would like to thank the organizer for giving me the opportunity to talk about the Concerto project on behalf of the Concerto collaboration. So, as Alessandro said, the Concerto instrument is composed of two matrices of kinetic and distance detectors, two kits here, and they are mostly based on the work that was done on the Nikka 2 camera. So the frequency range that we are sensitive of is between 120 gigahertz and 360 gigahertz with a high frequency sampling of 3.7 kilohertz. So the detectors operates at 70 milli-K thanks to the dilution cryostat in closed cycle, and with the help of two stages pulse tubes. So the critical difference between the broadband instrument like Nikka 2 is the additions of Martin puppet interferometers in front of the cryostat. And this consists of a series of mirrors, one of them being constantly sweeping between several positions at a few hertz, typically at 2.5 hertz. And that allows us to encode the spectral informations in the temporal domains. And with the best spectral binning of constant 1 gigahertz over the band, it provides spectral resolutions between 100 and 300. So as of last April, as Alessandro said, Concerto is installed on the Apex telescope. And for those who don't know that radio telescopes, it's located on the Chananta Plateau. This is the official aids. And it's Apex is a collaboration between different institutes, the Max Planck Institute for Radio Astronomy, ESO, and OZO. And the surface was upgraded in 2018, and they have an agreement for extending the use of Apex until the end of 2022. So the two Concerto arrays are actually observing the skies at different band passes, which we call low and high frequencies. And thanks to the Martin puppet interferometer, we can choose the spectral resolutions up to 1.2 gigahertz at the highest resolutions. As for any Fourier transform spectrometer, the instrumental line response will be a sync function, as for example in the case of the Herschel-Spire FTS for those who used it in the past. In those frequency bands, we can observe many things. At higher redshift, we will observe the C+ lines at a redshift greater than 5.2, or many CO lines at lower redshift, but we will also be able to observe dust continuum and free in local galaxies. So the project itself started a bit before 2016, when the first ideas were emerging, and it quickly gained momentum with the first dedicated fundings back in 2017. With the ERC funding starting in January 2019, we could start the construction of the instrument, and it was quickly followed with the Apex preliminary design review, and followed by the critical design review and the final design review in early 2020. At the same time, we were installing the KISS instruments that Alessandro presented before, which was basically a pathfinder for the Concerto technology. So it has a small mirror moving and everything. So in 2020, at the end of 2020, after two confinements, we had an intense in-lab testing here, where we could test the instrument in the configuration it would be installed at Apex. I will come back to that later. And we had an installation early April, installation of the instruments and the science verifications. And nowadays we are in science observations. And actually, I can even prove it to you, we are actually observing on sky right now. So I am the backup observer for today. So I can show you the acquisitions here. So I cannot resist showing you a few pictures of Concerto. So the first one was in June 2029 with these two parents. So you can see Alessandro and Beelen in front of the cryostat, which just arrived in Grenoble. And at that time, I can recall that the cryostat was actually leaking. So there were lots of activities already on this side. Half a year later, in January 2020, we had the first mechanical assembly. So you can still see the cryostat in the back here, in the background. In the middle part is where the sweeping mirrors will take place. And in the front here, you see mostly the readout electronics racks, which are mostly empty at that time. And the mechanism here to move the M3 mirror in the cabin. So that was in January 2020, and a few confinement later, you could see the fully integrated instrument here. So you can still see the chassis that I was showing just before with the cryostat here, and on top of that, the optical box, the so-called optical box, which allows to takes the light from the sky and put it into the moving mirrors and the cryostat. So what you can see also in these pictures is here the what they call the planet simulator. So that's basically a small piece of a small sphere of metals in front of a cold background, which we could observe thanks to this mechanism and try to test all the Concerto subsystems. And we did observe this source in the lab. So that was the first light in the 16th of November in 2020. So you could detect the metal sphere here as well as the cables holding the sphere. We had also some spectroscopic tests where we could observe the interferograms changing in the same way as the photometry when we were crossing the planet. So after this intense testing, the shipment occurs to Chile, and there is also already a story made by Ulysse, the logistics service from the CNRS, which makes the news. It's quite interesting. I encourage you to read it. And in the meantime, the APEX staff had to remove the Laboca instruments, which were taking most of the space in the C cabin at APEX. So you could see it was pretty empty at that time, but the installation of Concerto started on the April 6th. And quickly, we moved in the different parts of Concerto, so it's two different parts, and we even had to cut some part of the optical box here. You can see that they were grinding the optical box such that it could fit, because Concerto is a big instrument and it's taking most of the space in the C cabin. And that's basically the end of the installations on April the 14th. Everything was in place, except here maybe for the M3 mirror, which is missing here, and you can see the optical box on the left, and the chassis with the cryostat at the end. So everything was ready on April 15th or 14th. The instrument was called, and we could not resist to make the first flight observations on the next day. And what you can see here is the timeline of 4 different kids. So you see the amplitudes of the signal which is received in versus time. And what you can see here is that we do detect the moon actually, and the moon is when actually the receivers are losing the resonances, so they are doing crazy things here. So 15 days later, we could do the first remote observations, because we knew that in the coming months we would have troubles to get access to the telescopes. So we had to test the remote observing possibilities. So people from Europe did observe the Catspaw Nebula for many different scans, and the image which is shown here is basically 16 minutes of integrations over a few arc minutes square, and it quickly demonstrated the mapping potential in imaging from Concerto. So all the faint structures that you can see in this image are actually true, and they are confirmed by other instruments like Artemis, Herschel, or Scuba observations. And this image was actually made by ESO, combining the Concerto observations here and in the background optical data from Vista. So overall, the instrument is fully functional, with 90% of the design kits seeing the sky or actually showing a beam, and you can see the different the different positions of the kids on the sky. And the sensitivity is, the rough estimate of the on-sky sensitivity is quite in agreement with what we had in mind based on the NICA 2 projections at the beginning of the experiment. Of course, nothing is perfect, and we identified a few problems. One of them being a so-called 50 Hertz optical noise, which we see in the data. They seem to originate from one of the cooling system towers from Apex, but that's still unclear how the coping is going on with the kids. We do have some interferogram stability problems, as it was mentioned, and we are working on that. And we did discover an optical aberrations on some part of the array here, which displays a larger aberration in the beams. But nevertheless, we could detect some of the sources, and this is here quasars, pointing quasars, which were observed for a few seconds here. So the main motivations for the Concerto instrument was to make a survey of intensity mapping for the C+ lines, and I'm going to try to explain why we wanted to do that. So you can see in that plot the Madao plot, which basically shows the star formation rate density as a functions of redshifts. And we know the contributions of optical galaxies and dusty star-forming galaxies up to a redshift of 2 or 3. Beyond that, it's quite unclear what is the contributions of the dusty star-forming galaxies to the overall star formation rate density, even with newer data. And the Concerto survey using the Concerto instrument is basically trying to get a census of the contributions of the dusty star-forming galaxies to this overall star formation rate density. To do that, we need to have a tracers of star formation at that redshift, and the most obvious one is the C+ line because it's very bright. And of course, we will not be able to detect individual galaxies in C+ at those redshifts. It's already quite difficult with ALMA, so do not even imagine with Apex. But we will use a new observing technique, which is called intensity mapping. And intensity mapping doesn't try to detect individual sources at those redshifts, but rather try to detect the overall emissions at different scales coming from those lines. And based on different scenarios for the star forming rate densities, so the optimistic, the pessimistic, and something in between, we made predictions using the numbers that you can see here based on NICA2 for the instrument. We make predictions of how well we would detect this power spectra coming from the C+ lines for different types of scenarios. And even at redshift 6 for the C+ lines, we should be able to detect the emissions on the power spectra with high signal to noise. So with the C+ power spectrum detections, we will be able to constrain the dusty star forming rate density and the typical hollow mass for star forming galaxies at redshift greater than 4. But also using the shot noise, we can constrain the faint number counts of C+ emitters as a function of redshift, because we will be able to detect the C+ at different redshifts. And for the individual sources, the very bright ones, we should be able to constrain the bright and luminosity functions using those sources. So the real treasure of intensity mapping comes with doing cross correlations with, for example, galaxy surveys, cosmic infrared backgrounds, anisotropies, or any other probes that you want to study. And also, we could be able to do internal cross correlations between the different frequencies of Concerto at a given redshift. And for example, we could think of cross correlating O1 and N2 that would allow us to do physics of the ISMs in the mean sense at those redshifts. So for example, the ratio between O1 and C+ would be the interstellar radiation fields measure and the mean density of PDRs at the different redshifts, at those high redshift. Or you could also think of the ratio between N+ and C+, that would be the fractions of C+ coming from ionized medium. So some studies were made, for example, here, trying to do cross correlations between C+ and O1. And you could see that we should be able to detect, we should be able to detect those cross correlations at different scales and study those mean values. But of course, there are some challenges. So given a line of sights, we will be looking at the C+, but also all the CO lines coming from lower redshift galaxies. So if you observe the C+, which is redshifted into the observing windows, we will also observe all the CO coming from lower redshift galaxies. And you can see here an example. If you have the C+ at a redshift of 6, you will also get the CO at the redshift of 2. But hopefully, we are observing on a very large frequency bands, and you can see that we should detect many different lines of the CO, not detect, but we will have in the data sets lines of COs at different transitions, And by doing cross correlations between power spectra of CO lines and C+, we can do foreground separations of those Z equals 2 galaxies with respect to the Z equals 6 C+ emissions that we want to discuss. So nevertheless, Concerto is a multi-purpose instrument with a large field of view and a low frequency resolutions. So this is a perfect bridge between targeted high resolutions, spectral resolutions instruments like the one that we are used to, and broadband photometry like NICA2 or even Planck or Spire. So we have identified a few science cases which could be where Concerto could be very interesting, like the Zenayev-Zeldovich effect observations, or even maybe gravitational lens IZ galaxies, local or high redshift galaxies, which could be an interest for the PCMI, or even star-forming regions, high altitude cirrus clouds, as it was demonstrated by this Cat's-Paw Nebula or the Crab Nebula, which were observed during the science verification. So as for the local galaxies, we could think of observing low JCO lines if they are bright enough. So that could be an insight of the reservoirs of molecular gas in those galaxies, or even at higher redshift for the higher transition lines. And in the continuum, that's where most of the things could be very interesting. You could have dust and gas mass, study the ratios between the two, or even probe submillimeter excess emission in the SMC and the LMC. And I think that Caroline Bott did some studies on that. I don't know if she's here today, but she could discuss that later. Or, for example, a complete follow-up of the Herschel dwarf galaxy survey in long wavelength. Closer to us, Concerto is very well suited for all kind of dust property studies in our galaxies, in particular dust emissivity, dust mass, dust temperature, because you will basically be able to detect the dust continuum spectrum in a very wide band. And we could even try to detect lower CO transitions like 2 to 1 or even 3 to 2, but of course without the high spectral resolutions as for the CDGISM, I think the Atlas-Gal follow-up, but on a much larger area. For example, I'm showing here the galactic plane regions, one galactic plane region is observed by Herschel, and you can, if you know the region well enough, you can recognize that here it's the Cat's-Paw Nebula, and the observations from Concerto that I've shown earlier is basically just this region in 15 minutes. And imagine that you could do that everywhere on that field. That would allow you to really understand what are the differences in the dust emission in the different regions of this map. So Concerto is an open instrument, and so far we had 2 observing periods. The first one is the P108, the ISO P108, which were not open to the community, but open to the Concerto collaborations. And we had the 2 proposals. The first one on the Cosmos field, so that's the main goal of our project, the intensity mapping on the Cosmos field. And we had an accepted proposal on the Zenayev-Zeldovich effects on one cluster on the ISO time, which have been observed. And on the Chilean time on this period, we had some open proposals because they did open Concerto to their community. In ISO P09, we had many proposals in the pipeline, so it's not yet accepted. It's they are processing them, I guess. Several SZ proposals, but also spectroscopy imaging of the Crab Nebula, astronomical reference targets. Maybe Xavier will talk a bit more about that later. And also a very large proposal, not a large, but a big proposal on galactic high mass star formation, which is there. I'm showing here the amount of data that we had so far. So it's going up quickly, very quickly, and we are observing right now, and we are getting more and more data. We are hoping that Concerto will be open in the next call for proposal in P110. So your proposal can get there, and we can propose to help you on the technical parts if you need to. So to summarize the project, Concerto, it's basically 2 kids array with Martin Pogon interferometer in front of it. And the main goal of the Concerto instrument, so the Concerto project, is to measure the C+ power spectrum at redshift greater than 4.5. And this intensity mapping is powerful to prove obscure star formations there at those redshifts. So we will hope to answer some of the questions at those redshifts. So there are some challenges on the way, but also some opportunities. And I leave you with 2 pictures. That was at the acceptance of Concerto by Apex, and just after the science verifications when we had a small hike in Marseille. Thank you.
So there was a question on the Google Doc that was related. So, do you have any questions?
I have one. So Alex, you said that I guess the Concerto team is asking to observe high mass star formation regions. Can you be more precise? Which one?
So it's not actually this you are referring to this proposal.
Yes.
So that's an open time proposal by Annie Zavagno, and you can ask her if you want to have the list of targets.
The comment by Claudia Ciccone was about the future of Concerto, considering Apex shutdown, I'd say. So what is the schedule for that?
So we do have an agreement to be able to complete the 1,200 hours of observations on the Concerto project. Apart from that, Concerto is open to the community as long as ESO is within the Apex consortium. After that, it's a big question. So there are many different possibilities. Some people, I don't know if you were aware, but some people were proposing to buy ESO time, I mean Apex time on Sky, writing a big check to the Apex consortium. That's not clear yet because we tried that to see if it was possible. We don't have a clear answer. For Concerto, the instrument, that's an open question also. We can discuss with Alessandro, but either we will have to remove Concerto if ESO says that we are not allowed to stay at the telescope, this is for sure. Mm-hmm. We do with the instrument afterwards. There are many possibilities. Either we find a new telescope, there is Yamaha close in Peru, close to it, if it's getting commissioned someday, or even somewhere else. So that's really an open.
Can't you get an agreement with MPI?
It's very difficult. It's very difficult.
Okay, so thank you.